Okay, students. So today's topic is Today's first topic is oxidation of alcohols using cheminophore. Okay, so this is our cheminophore. This is in cheminophore K positive. It is just a spectator ion. Okay, the spectator ion does not take part in the reaction. It's just a spectator ion. Okay, this is the this is the structure of this cheminophore. K is just the spectator ion. Okay, and MnO4 double bonded to three oxygens and single bonded to one oxygen. The oxygen having a negative charge. Okay, so uh, this is the main part which takes part in the oxidation process. Okay, we'll discuss the mechanism. We'll discuss two mechanisms: secondary alcohols reaction, oxidation of secondary alcohols using cheminophore, and oxidation of primary alcohols using cheminophore. Okay, so first we are going to discuss about oxidation of secondary alcohols using cheminophore. Already I had drawn these structures just half an hour ago. Okay, so we're going to discuss these reactions. See, this is our manganese oxide. Okay, this is our secondary alcohol. This in this manganese oxide, this double bond pi bond collapses to the or goes to the oxygen. You can see here oxygen. This becomes a positive center. Okay, so this oxygen from the alcohol, it can easily attack the manganese atom. Okay, and it bonds the manganese. It bonds with the manganese. You can see here, and it gets a positive charge. It gets a positive charge. So this oxygen, which is bound to the manganese, this oxygen is able to abstract this hydrogen, okay, from this hydrogen oxygen bond. This bond breaks, and these electrons goes to the oxygen to neutralize this charge. Okay, so we can see here the oxygen gets neutralized. Okay, and this is our, we have a alpha hydrogen here. So this oxygen which is present on the this oxygen bound to the manganese, it abstracts this hydrogen, alpha hydrogen. Okay, and this bond breaks, this bond goes to the oxygen, it becomes doubly bonded. Okay, and this bond breaks and collapses to the manganese. This bond breaks and collapses to the manganese, and we get a product, ketone. So we can say secondary alcohols are converted to ketones. Secondary alcohols get converted to ketones. Secondary alcohols get converted to ketones. Did you understand? Secondary alcohols get converted to ketones. Lakshmi Chaitanya. Hello?
Yes, sir.
Hello?
Yes, sir.
Okay. Secondary alcohols, they get converted to ketones. The secondary alcohols, they get converted to ketones. Okay. Now we come to primary alcohols. This is our primary alcohol. I have, for simplicity, I have shown these two hydrogens, these two alpha hydrogens. For simplicity, I have drawn these two alpha hydrogens. Okay, these two alpha hydrogens I have shown for simplicity. So this is our ethanol. This is ethanol. Okay, this is ethanol. a primary alcohol. Okay. Now the same thing happens. The this potassium, this permanganate ion, the oxygen attacks the manganese atom, and this pi bond goes to the oxygen. This pi bond in one of the oxygens, in one of the oxygen, this goes to the oxygen. This pi bond goes to the oxygen, so it gets a negative charge. Okay, and since this oxygen makes a bond with manganese, it gets a positive charge. It gets a positive charge. So this oxygen which is bound to the manganese and having a negative charge, it is able to abstract this hydrogen. It is able to abstract this hydrogen. Okay, and this bond is broken and goes to the electrons go to the oxygen to get to neutralize it. Okay, so we get this structure. Okay, this structure. So this oxygen, the other oxygen having a negative charge, is able to abstract one of the alpha hydrogens. One of the alpha hydrogens, this bond breaks and goes to the oxygen. Okay, can you see? This bond breaks and go to the oxygen. It becomes a double bonded. Okay, and this bond breaks from the oxygen and collapses to the manganese. So we get final product. We not final product. We get an aldehyde. This is an aldehyde. This is an aldehyde. I'll write here aldehyde. Okay, so we get an aldehyde here. Still we have a hydrogen, so it can go for a further oxidation. It will not stop here. The reaction will not stop here. It will go for further reaction. So what happens? From the solution, a base will attack the carbon atom, which is partially positive. It has a partial positive charge. This carbon has a partial positive charge. Okay, and this has a partial negative charge. Or we can say here, if this pi bond goes to the oxygen and it becomes a negative. Okay, and this becomes a electrophilic center with a positive charge. It becomes a electrophilic center. Okay, so because oxygen is more electronegative than the carbon, so this bond goes to the oxygen, it becomes a negative, and this becomes a positive carbocation. So electropositive center. So this base attacks this electrophilic center. Okay, you can see here, and this base, it forms this compound. Okay, now we have oxygen with negative charge, which it can participate, it can attack the permanganate ion, so it again it attacks the manganese atom, and it bonds with the manganese. Okay, here it bonds with the manganese, again getting a positive charge. It gets a positive charge since it has donated its a pair of electrons for bonding, so it gets a positive charge. Okay, so this, okay, there is a mistake. It does not get a positive charge since already it has a negative charge, so it can donate this pair of electrons for the bonding. So it makes a bonding with the manganese atom. Okay, now this alpha hydrogen, it gets abstracted by one of the oxygen atoms having a negative charge. One of the oxygen atoms present on the manganese having a negative charge, it gets abstracted. This hydrogen gets abstracted. Okay, this bond, carbon hydrogen bond, gets broken and this bond goes to the oxygen. This bond goes to the oxygen. Since this bond goes to the oxygen, this bond collapses back to the manganese. This bond collapses and goes to the manganese. Okay, so we can see here we get a product. This you can see here CH3 C double bond O, CH3 C double bond O, OH. Okay, so this we get a final product. So primary alcohols get converted to the carboxylic acids. Primary alcohols, they get converted to carboxylic acids. Primary alcohols, they get converted to carboxylic acids. Did you understand? Okay. So our next topic is reduction of carbonyl compounds using lithium aluminum hydride and sodium borohydride. So before discussing the mechanism or the reactions of lithium aluminum hydride and sodium borohydride with carbonyl compounds, we must understand what are reduction reactions, or what is reduction. As we had discussed oxidation, so reduction is opposite to oxidation. Reduction is opposite to opposite to oxidation. Reduction. Reduction is reduction. So in reduction, addition of hydrogen and removal of oxygen. Addition of hydrogen or hydrogen atom. Addition of hydrogen and removal of oxygen. So this is called reduction in terms of organic chemistry. We are not discussing about electrochemistry. Okay, what is reduction? Loss or gain of electrons or loss of electrons. We are not talking in terms of gain of electrons or loss of electrons. We are talking about gain of hydrogen ion, gain of hydrogen atom, or loss of hydrogen atom or oxygen. Gain of hydrogen or loss of hydrogen, in this term we are talking about. Okay, so in reduction, what happens? In the molecule, there is addition of one or more than one hydrogen atoms, or removal of oxygen atom from the molecule or the substrate. Okay, so first we are going to discuss, we have to discuss about lithium aluminum hydride and sodium borohydride. So we'll see the differences between lithium aluminum hydride and sodium borohydride if you want. We have lithium aluminum hydride. Lithium aluminum hydride and sodium borohydride. Sodium borohydride. Okay. Lithium aluminum hydride is a very strong reducing agent. Lithium aluminum hydride is very strong reducing agent. This lithium aluminum hydride is a very strong reducing agent. Mute yourself. Rule number 55. Okay, so this is very strong reducing agent. Strong strong reducing agent. It can reduce aldehyde, aldehydes, ketones, most of the carbonyl compounds. It can reduce most of the carbonyl compounds. This one, sodium borohydride, is a weaker reducing agent compared to lithium aluminum hydride. Weaker reducing agent, weaker reducing agent compared to lithium aluminum hydride, compared to lithium aluminum hydride. So we'll discuss why lithium aluminum hydride is a stronger reducing agent and sodium borohydride is a weaker reducing agent. Okay. Okay. We'll discuss why lithium aluminum hydride is a stronger reducing agent and sodium borohydride is a weaker reducing agent. Okay. So we'll draw the structures. Aluminium, and this is boron. Okay. Now one, they aluminum forms three bonds and boron also forms three bonds, but one extra hydrogen is bonded to aluminum and it gets a negative charge, Similarly, here also this boron is bonded to one extra hydrogen atom and the negative boron gets a negative charge. Okay. Now, till now it looks similar. So what is the difference? Where is the difference? Aluminium is less electronegative than boron. Aluminium is less electronegative than boron. You can write here. Aluminium is less electronegative than boron. If we see the periodic table, electronegativity increases, size here increases. Electronegativity increases from left to right, and the size increases from here to here. Okay, size. So boron, aluminium. So this boron is more electronegative than aluminium. Boron is more electronegative than aluminium. Now, since boron is more electronegative than aluminium, if we see here, okay, this hydrogen is more electronegative than the boron. Hydrogen is more electronegative. So it becomes a polar bond. Since this is the this is one extra boron gets has an extra hydrogen bond, it gets a one negative charge. Okay. And this this bond, because boron is more electronegative than aluminium, so this bond is shorter compared to this bond, aluminium hydrogen bond. This boron hydrogen bond is shorter because of the difference in the electronegativity. So this bond is shorter and stronger. Short, shorter. This bond is shorter and stronger. This bond is shorter and stronger compared to this bonding in this aluminum hydride. Bonding in aluminum hydride. Okay. So this bond is shorter and stronger, but this bond this bond is longer and weaker. This bond is a bit longer and weaker. Longer and weaker. So it means the hydrogen can easily break away. This hydride ion, which is a strong base, can easily break away from this lithium aluminum hydride. Okay, so this hydride ion can easily break away. This hydride ion can easily break away from this bond. This, okay, this having a negative charge, which is a strong base, which is a strong base, strong base, strong base. Here also it breaks, but it is not easily. It does not break easily. It does not break easily. Okay, but here it breaks easily. Okay, so that is why lithium aluminum hydride is more strong reducing agent compared to sodium borohydride. Compared to sodium borohydride, lithium is just an spectator. It's just a spectator ion here, and here also sodium is just a spectator ion. Okay, for balancing for neutrality. Okay, this is just a spectator ion. So we are mainly concerned with this aluminum hydride and boron hydride. Okay, so in this case, this bond is longer and weaker. So this one of the hydrogen atoms can easily break away, and they form hydride ion, which are strong bases. Hydride ions are strong bases. Same thing happens here, but they the break. They this bond breaking is uh, somewhat tougher than compared to this one. Okay, so that is why lithium aluminum hydride is stronger reducing agent compared to sodium borohydride, just because of the difference in the electronegativities, just because there is a difference in electronegativities. Understood? Did you understand? Hello? Hello?
Yes, sir.
Did you understand why lithium aluminum hydride is more stronger reducing agent than sodium borohydride? Hello?
Yes, sir.
Okay. If you have any doubt, you can ask. Now we'll move to the first reactions, reduction of carbonyl compounds using lithium aluminum hydride. The first we'll discuss about this reduction of carbonyl compounds using lithium aluminum hydride. Right here. Reduction of carbonyl compounds using lithium aluminum hydride. Okay, so first we'll discuss about this one.